This video lecture is meant to cover the information found in Chapter 10, Section 1, pertaining to moles. In the last lecture, we talked about particles, representative particles, being either atoms, molecules, or formula units. And we also talked about counting by weighing. So we're continuing that discussion today, but with more specific to the chemistry realm. On the periodic table, there's an atomic mass written for each element, and the average it represents the average atomic mass for all the isotopes of that element. And it has a unit of AMU, which stands for atomic mass unit. Essentially, one atomic mass unit is equal to the mass of one proton or one neutron. So when we talk about the atomic mass, we are talking about the average mass of a single atom. For carbon, the average atomic mass is 12.011 to 5 significant figures. If we round that to the nearest tenth, it's 12.0 AMU per atom. Hopefully you can see that this is a very small mass, and it would be very impractical to work with one atom of carbon. A more useful measure of mass for humans to work with is grams. What if we weighed out 12 grams of carbon atoms on our scale? So taking that atomic mass from the periodic table of 12.0 for carbon, and taking that number and weighing out exactly that much mass in grams of that element on a scale, like so. The question is, in that 12.0 grams of carbon, how many atoms would there be? Clearly, there would be more than one atom of carbon in there. It turns out that the answer is a very specific number, 6.02 times 10 to the 23 atoms of carbon. That's 6.02 times 10 to the 23rd. This is a very, very large number, but it's a very unique number to chemistry. Let's consider a different element. Let's take, for example, helium. Helium on the periodic table has an average atomic mass of 4.0026. That's to 5 significant figures. What if we said, let's make it a little simpler here, and what if we weighed out 4 grams of helium atoms on our scale? How many atoms of helium would that be? Clearly more than one atom, but it turns out that the answer is also 6.02 times 10 to the 23 atoms of helium. Any element on the periodic table, I'm picking silver here. Silver has an atomic mass of 107.87 AMUs. If you weighed out 107.9, again that's a rounded number to the nearest tenth, 107.9 grams of silver atoms on that electronic scale, how many atoms would there be? You got it. There's going to be 6.02 times 10 to the 23 atoms of silver. The question is, where does this number come from? Why is it the same for each element? Well, as you already know, 1 AMU is equal to 1 proton, which is equal to 1 neutron. It turns out that the mass of 1 AMU is 1.67 times 10 to the negative 24th of a gram. So we know the mass of a proton. It's a very, very small number, and that makes sense because a proton is a very, very small particle. If we were to use carbon as the example, we know that one carbon atom weighs 12.0 AMUs. So how do we find the mass of that one carbon atom, not in AMUs, but in grams? Well, to do that, we'll start with the average atomic mass for carbon, which is 12.0 AMUs per atom, and we know that each atom weighs 1.67 times, or not one atom, but each proton and each neutron weighs 1.67 times 10 to the negative 24th grams per AMU. When you multiply those two numbers together, the AMUs will cancel, so you'll end up with a unit of grams per atom. And if you punch this into your calculator correctly, you'll get the number 2.00 times 10 to the negative 23 grams per atom. Okay, so this is the mass of one carbon atom in grams. It's a very, very small number. And again, this should make sense because a carbon atom is a very, very small particle. But what if you didn't have just one carbon atom? What if you had 6.02 times 10 to the 23 atoms of carbon? How much would it weigh in grams? Well, we know the mass of a single carbon atom in grams. Let's take this mass of a single atom and multiply it by this number of atoms. So 6.02 times 10 to the 23 carbon atoms times 2.00 times 10 to the negative 23 grams per atom. And what you end up with, if you punch that into your calculator correctly, you end up with 12 grams. So it turns out that this 12 grams is the mass of 6.02 times 10 to the 23 atoms for carbon. If you did this mathematical proof for any element, it would always work out that 6.02 times 10 to the 23 atoms will have a mass equivalent in grams to the atomic mass on the periodic table. This number, 6.02 times 10 to the 23, is referred to as Avogadro's number. It is also referred to as a mole. You've heard this word mentioned numerous times in class before. We really haven't discussed what it meant. But a mole is a number, like a dozen. When you hear the word dozen, it's just a word that means a very specific number, and of course it means 12. In chemistry, if we use the word mole, we're talking about the number 6.02 times 10 to the 23. So a mole in chemistry is a unit. Of course, it's not the animal. That's supposed to be a joke. Right? So the take-home message is that if you have 1 mole of any object, usually we're referring to atoms or molecules or formula units, but if you have 6.02 times 10 to the 23 atoms, you have 1 mole of them, and you will have 6.02 times 10 to the 23. So, to summarize, if you take the atomic mass from the periodic table, in this case we've got silver at 107.87, and if you weigh out that number in grams on the electronic balance, 107.9 grams, okay, again I've rounded that to the nearest tenth, but in that sample of silver that weighs this much, 107.9, which is the number we got from the periodic table, we'll know that in this sample of silver, we will have 6.02 times 10 to the 23 particles, 1 mole of particles in that sample. This is what we call molar mass. It's the mass of 1 mole of a substance. Every substance will have a different molar mass because, of course, each element weighs a little different. That's evident as you see that on the periodic table. Molar mass, defined as the mass of 6.02 times 10 to the 23 objects. You'll find the molar mass on the periodic table. It's the number with a decimal. It's the average atomic mass. We're going to round those atomic masses to the nearest tenth. That's just for convenience sake. And the unit is going to be grams per mole. Now, of course, you know that G is the symbol for grams right here. And you wouldn't think so, but the unit of mole, M-O-L-E, is abbreviated as M-O-L. I know it seems ridiculous because the word mole is not very long. It shouldn't need any abbreviation, but it does. So grams per mole is the unit of molar mass. So to find the molar mass of an element, you will need a periodic table. So please take a moment to pause the video, find a periodic table that you can refer to. Okay, you paused the video, right? And you did go get that periodic table? All right, find helium on the periodic table. Its atomic mass is 4.0 AMUs, which means its molar mass is 4.0 grams per mole. If you weigh out 4 grams of helium, you will have 1 mole of helium atoms, 6.02 times 10 to the 23 atoms. Oxygen on the periodic table We're going to round all these molar masses to the nearest tenth. We'll have a molar mass of 16.0 grams per mole. Lead will have a molar mass of 207.2 grams per mole. Pretty simple, because all you have to do is just look up the elements on the periodic table and the molar masses are evident. You have to do a little bit more work, however, when you're finding the molar mass of a molecule or a formula unit, because it's not just a single element. So you have to factor in how many atoms there are in that formula. So for example, hydrogen gas, H2. If you look up hydrogen on the periodic table, its atomic mass is 1.0. But in the formula for hydrogen gas, which is H2, there's 2 hydrogens. So you'll have to multiply 1.0 times 2 to give you 2.0 grams per mole. That one's pretty simple. Let's up it a little bit, the difficulty. Water, H2O. There's 2 hydrogens and 1 oxygen. So we know the 2 hydrogens will weigh 2.0, but then we have to add the mass of the oxygen. Oxygen is 16.0. There's only 1 of them, so the mass from the oxygen is 16.0. So if you add those 2 numbers together, you will of course get 18.0 grams per mole. So the molar mass for water is 18.0 grams per mole. Calcium chloride, CaCl2. There's 1 calcium. It has a molar mass of 40.1. There's only 1 of them, so the mass from the calcium is just 40.1. Chlorine. Each chlorine weighs 35.5, but there's 2 of them, so multiplied by 2 you get 71. Adding those 2 numbers together, the molar mass adds up to 111.1 grams per mole. C6H8O7. Each carbon weighs 12.0, but there are 6 of them, so the mass from the carbons is 72. There are 8 hydrogens, each weighing 1, so the mass from the hydrogens is 8. There are 7 oxygens, each weighing 16, so the mass from the oxygens alone is 112. If we add those 3 numbers together, we get a total molar mass for this substance to be 192.0 grams per mole. Ki. Potassium has a molar mass of 39.1. Iodine has a molar mass of 126.9. Adding those 2 together, you get a total molar mass of 166.0 grams per mole. Mg3PO4 There are 3 magnesiums, each weighing 24.3. Now here, take a close look. How many phosphorus atoms are here? There's 1 inside the parentheses, but we need to distribute that 2 through. So there's 2 phosphorus atoms and a total of 8 oxygen atoms here. So if we consider the phosphorus, each phosphorus weighs 31.0 times 2 is going to give us 62 from just the phosphorus. There's 8 oxygens times 16 will give us 128 from the oxygens. All told, if we add up those 3 masses, it adds up to 262.9 grams per mole. So all of the molar masses we've been talking about is the unit. Think about the unit. It's the number of grams per 1 mole. But what if you don't have 1 mole? What if you have more than a mole or less than a mole? Well, that means you're going to have more than 6.02 times 10 to the 23rd or less than 6.02 times 10 to the 23rd. So think about it. It's really just a mathematical ratio. If 1 mole is equal to 6.02 times 10 to the 23rd, if you have half of a mole, how many things will you have? Well, you'll just have half of this number. Half of 6.02 times 10 to the 23rd is 3.01 times 10 to the 23rd. What if you had 2 moles? How many particles would you have then? Well, 2 moles, double this number, you'd get 12.04 times 10 to the 23rd, which is an accurate number. It's just not good form. It's not scientific notation. So if we were to move this decimal over so that it's between the 1 and the 2, that changes the value of our exponent. So 2 moles is 1.204 times 10 to the 24.